Thank you very much for being here. And I want to start by thanking Professor Nuno Martins for inviting me and for his warm welcome, and also Professor Chelapa from the department who subscribed also the invitation. This seminar is about modeling and control of anesthesia. What I'm going to tell you is a pass in the last 26 or 27 years that I've done in this area. Of course, I was not alone. It was a long pass, so throughout the years, many people helped me, some professors, several medical doctors, and some students, many students at different levels. I want in particular to highlight Professor Teresa Mendonça from the Faculty of Sciences of the University of Porto, and she is in a group that has a long tradition in this area and did a lot of effort to create a structure, an experimental structure in connection to two hospitals in Porto, the Hospital of Sant Antonio and the Hospital Pedro Hispano. Without this work would be empty. Okay. In the past 8 years, although some of the results have been obtained earlier, we have been supported by these 3 projects, national projects. So my presentation plan is divided in 3 parts. First, I'm going to speak about the models of anesthesia. What are the models? A model is very simple. Is a Wiener type model. Okay, but then we can add some extra things. And then the second part is addresses one problem that appears in virtually all control problems that have to do with life, which is variability and uncertainty. One person, one individual, be either one human person or an animal, is completely different from the other. So how can we, what is the impact of this on models? How can we study it? And how can we tackle these difficulties? And the third part is closing the loop. I mean, how can we take decision? And how can we actually act on the systems to modify their behavior? So let's start to speak a little bit about models for anesthesia. First of all, what is anesthesia? In particular, general anesthesia. Many of you probably have gone to the dentist, which is a very bad experience, and you receive some form of anesthesia when he's doing some painful things. So anesthesia is not just that. And I'm speaking of a different type of anesthesia. That's local anesthesia, the one that you receive. I'm speaking of a type of anesthesia in which your body is placed in a different state of the normal state in which we are, and is prepared to undergo stress. Okay? Big stress. I'm speaking more about that in a moment. Then I will speak a little bit about the types of models. You can say something, you can divide the models into parts. The pharmacokinetic part and the pharmacodynamic part, which is not listed here explicitly, but it will be addressed in these C and D parts. Pharmacokinetic is when you infuse a drug, what happens to the drug in the body? What do your body do with the drugs that you take? And the pharmacodynamic part, which will be addressed in part C and D, is what the drug does to the behavior of your body. So it's a converse. Okay? And we are going to address two important parts of anesthesia, which is neuromuscular blockade, you become paralyzed, and hypnosis. You lost your memory, you lost your self-consciousness. Okay? And also you lost your pain. Why have I not individuated pain here? Because you can't control it. You don't have yet commercial sensors. There are experimental sensors. We'll speak a little bit about that later. Okay? I understand that there are some PhD students here, and if they are curious about this, there is in last December issue of IEEE Control Systems, there is one paper in which these things are explained as better as I could. Okay. So, what is general anesthesia? You have three components. One of the components is that you cannot have involuntary movements. You cannot start to move even if you are asleep. If the surgery is a surgery to the eye must be kept still. Because if the eye has involuntary movements, it can cause problems to the surgeon and accidents. Okay? In general, you must stand still. Okay? So the other thing is, as I mentioned before, hypnosis. Placing the individual in a state of unconsciousnness, and I call it depth of anesthesia. I represent, when I say DOA, it's depth of anesthesia. When I say NMB, is this areflexia. Areflexia is the state of you cannot have involuntary movements. Okay, and this is achieved by blocking the nervous impulse from your nerves to your muscles. So it's neuromuscular blockade. And then the third component is analgesia. You don't feel the so-called noxious stimuli, the pain. You don't feel pain, or you don't react to pain. Okay? Of course, the state of the person is more complicated, and the surgeon must supervise the person and ensure that his state is correct. The state comprises the mean arterial pressure, the gas components that the patient is exhaling, and so on. The heart rate, it's 4 or 5 or 6 components. Okay. Let me show you some pictures. The pictures I'm showing to you, they are not so good, but they have the advantage that probably the interest that they are taking from the projects. Okay, so this is not just for the picture, it's what happens during projects. This was taken at a veterinary hospital in Portugal, and you can see some equipment. You can see searing pumps that you use to infuse some drugs in the patient. Okay, so you can in surgery you can use two types of drugs. You can have gaseous anesthesia, or you can have intravenous anesthesia, where you inject something on the blood circulation. Okay, I'm speaking about the second one. Although the first one, there is also a rich literature on control. So you can see here dosing equipment, a gas dosing device, and this is so the two actuators for these two situations. Okay, but we are going to concentrate on this one. Another aspect, this is in the operating theater. The surgeon is looking at the surgeon, and actually this is a position that everybody can look in the operating theater. And you have a number of records, of variables. You have important numbers here. I will detail it a little bit later. You can see here two syringes. Okay, one is for the drug that causes neuromuscular blockade, and the other is for the drug that causes loss of unconsciousness. Of course, there is a third one concerned with analgesia, which is not shown here. And this is your familiar, at least to most of you, MATLAB. Okay, so we have a computer, ordinary computer, and you can connect the computer via the USB port to the syrinx. Okay, and this is software developed to monitor and allows you to give orders to the syrinx and to visualize signals. You can say, but this is not reliable, for God's sake. Well, it's no problem. If there is a problem with the computer, the anesthetist can operate right from the syrinx, as he usually does, manually, and see the signals in other places. So this is a way that allows you to have everything centralized. Okay, it's not critical. The safety issues were taken care very, very seriously by the engineers and by the medical doctors, and we have a number of safety nets. Okay, if these systems fail, there is a backup system that allows you to continue things. Now, in general, if you think, well, I'm injecting a drug dose to the body. Okay, this is the input to your system. It's the variable that you manipulate. And you measure something, can be the neuromuscular blockade level or the depth of anesthesia level. Okay? And in between what you have a linear model that I'm breaking in two parts. The first linear model filters the drug dose and as its output the plasma concentration of the drug. Okay? And then this drug is passing from the plasma to the effect concentration. In some cases, they are both the same, or you cannot distinguish one from the other. Okay, but in general, this is the situation. So these are linear models up to a good approximation. Okay, and then you have a non-linear model. This linear model is the pharmacokinetic model. Okay. It's very well studied by the companies that produce the drugs. And this nonlinear model is a pharmacodynamic model. So if you have some concentration of drug in the effect compartment, what is its effect, for instance, on neuromuscular blockade? Okay? So let's speak a little bit first about this linear model and then about nonlinear models for NMB and DOA. For compartment models, for the pharmacokinetic models, one possibility is to use compartmental models. So you assume that your body is divided in compartments. Imagine containers with pipes, okay? And you have the central compartment and the peripheral compartment, okay? In the exchange, the central compartment receives, think of the central compartment as your plasma, so your blood, including the liver and so on. And think of the peripheral compartment as your fat and some other parts which are far away. Okay? And they change, and these numbers, these symbols here denote the rate of change. So this is like managing a grocery. Okay? In a grocery, you want to build a model for the mass of potatoes that you have. And the mass of potatoes is the amount that comes per unit time times the interval of time that you are considering, minus the amount of potatoes that you are selling per unit time. That's the same story here. Okay? Instead of potatoes, you have drugs. So you divide the time in intervals of delta t, and you say the amount of drug in compartment number 3 here, the effect compartment, at time t plus delta, is the amount of drug in time t plus the variation, and the variation is the rate of changes, which is proportional to the concentrations of the other compartments, times the interval of time. So by a simple manipulation, and by making delta go to 0, you just get this differential equation. Okay? Now, these compartment models have a number of facilities important because they have mass conservation. This is a positive system, and you can use Lyapunov stability concept. So there is a rich literature that designs controllers based on this. I've placed here the title of a book where you can see, but in particular, Haddad has done important, very huge bibliography by himself and his co-workers. It's impressive work. We are going to take another road. So I'm not assuming that the pharmacokinetic model is a mass conservation model or ensures positivity, but it's just a linear model, and you are relating signals. Okay, you lose some things, but you won in flexibility. Now let's speak a little bit about the nonlinear model that relates the drug concentration on the effect compartment with the effect. Okay, so, and I'm going to speak first about NMB and then about depth of anesthesia. We use normalized indexes. How can you measure your neuromuscular blockade? Or can you measure your degree of unconsciousness? You use an index. 0% in NMB is fully paralyzed. I cannot move. 100% is the state in which I'm here, moving a lot. Okay. In the same way, for depth of anesthesia, 0 is deep coma and 100 is normal wake state. In the end of this talk, you will be about 80%. I'm going to make you all sleep. Okay? Let's look at the neuromuscular blockade. Okay, so you have the termination of an axon, so of a nerve cell, which is a long cell, and this red part here is the muscle, and there is a cleft, so an interval, a space between two. Okay, this is the effect compartment. This is the effect compartment. This tiny part here, at the junction between the nerve cells and the nerve and the muscle cells. And what happens when there is an electrical impulse coming from the axon? This electrical impulse activates this calcium ion calcium channels that you see here, 3, but there are many more. And they started getting calcium ions that trigger this vesicle. You see these little balls? They inside have these red balls. They are acetylcholine molecules. And this migrates to the cleft, and they start liberating acetylcholines that travel through the cleft. Okay? And some of them meet their receptors here in some other channels, ionic channels, and these ionic channels pump sodium ions from one side and potassium ions from the other. So you create a differential of potential, and this forces the muscle to contract. Okay? So when you want to interfere in this process, you create neuromuscular blockade. Okay? And you can do it in 2 possible ways. These drugs, you can imagine why I've placed here an Indian, a Brazilian Indian, because Brazilian Indians discovered these drugs. They are the curare drugs. Okay? They paralyze. Maybe some of you have read, I don't know whether you did it or not, the novels by Emílio Salgari and the guys in the coast of Brazil in the 16th century, the stories of Caramuru and so on. Okay, and the cannibals, they use these little arrows with these curare poisons to paralyze their victims, and then they were beating with a stick to kill them. Okay, so this poison does not kill, directly, but paralyzes. Of course, when the person is paralyzed, he's no longer able to breathe. So even if his head is not smashed, they would be killed by not breathing. And you have two types of drugs, depolarizing drugs, which are slow in disappearing, so they have very long delay. So this is not good for control. Control is delay is an enemy of control. So when they started using non-depolarizing drugs such as atracurium, rocuronium, vecuronium, cisatracurium, there are many of them, is when control was made possible, because these are of fast absorption. So you give the drug, and the drug is absorbed fastly. The time constant is relatively fast, and this allows you to have some regulation ability. Now,
but these are not local in their effect, right?
Sorry?
These non-depolarizing drugs, like that you were mentioning, the fast-acting ones, they are not necessarily local.
No, they are global, because this is injected in your plasma, and it goes throughout the body. You became paralyzed. Okay, there are many novels about that. Now, why have I placed here the classical operational amplifier MUA741? To point out the following: if you want to model the neuromuscular blockade, of course you can start writing equations for all the processes I mentioned. The propagation of the electrical impulse, the gated ions, and so on. It's possible, and there are people that have done that. But in the end, you come out with a huge model, okay? And to parameterize this model would be a nightmare. In the 741, you have a similar situation. You have about 30 transistors, but you just say, okay, I don't care about the transistors. I only care that this behaves like a differential amplifier with a very high gain. That's it. And with that, we can make a lot of predictions. Okay? So this is a phenomenological model. You cannot interpret the tail of the inside, but you can use the circuit to connect it to other circuits. Okay? And here is the same. So instead of writing all the details, we assume that the relation between the concentration in the effect compartment is CE is related to the level of neuromuscular blockade through this equation. Okay? So if C is 0, you are at 100%. If C grows, it decreases. And when C is this parameter C50, you are at 50%. That's why this is called C50. So you have two parameters, C50 and this gamma. Actually, the curve is not exactly like that. It's a little bit S-shaped. Okay? Still, only with these two parameters, you have a lot of identifiability problems. That's another story that I'm not going to speak about. So you have to postulate a number of parameters. Okay, here you have a picture in the operating theater. You place some electrodes in the ulnar nerve, or in some other, usually it's in the ulnar nerve in the basis of the thumb, and then you measure by electrical or mechanical sensors the reaction of the muscles. And from this you can infer the capacity, the neuromuscular blockade level. Okay. I will skip this story of the sensors.
So you would do that even if you care about the NMB response elsewhere, for instance, the eyeballs or muscles elsewhere? I mean,
yes, I'm assuming that the measure in the thumb is representative of the state in the whole person. Okay, that's the state. It's not possible that you place sensors all over. Actually, in many cases, still recently, people were not instrumented. I mean, this story of instrumenting people for the operation is quite new. Okay, there are many hospitals throughout the world for sure in Portugal. I'm sure that also in the United States, depending on the hospital, in which you don't monitor the signals. Okay, but I'm assuming that and it's not. There are some problems, but we can discuss that. Sometimes the surgeon starts saying, well, the patient is moving. Okay, but we say, but our level is very low. So there can be problems of representativity. Okay, so these sensors are by itself a science.
But the other extreme is even more of concern, isn't it? That even if you achieve NMB very well, the concern about leaving the consciousness level high, and as a result...
That's another story.
Yeah, that's another story.
That's another story.
Sort of another kind
with
of...
another sensor.
Yeah.
With another sensor.
Yeah.
Okay? I'm going to speak about that. Okay? So for NMB, what we have, just to give you an idea of the dynamics, you have the linear part and you have the Hill equation. So when you have here a bolus, so an injection of drug, what happens is you have the impulse response here, we have the still filtered here, and the Hill equation is a kind of nonlinear inverter. Okay, so the person is at 100%, receives the bolus, the NMB goes down, and then the body starts to metabolize, and it goes up again. This is a simulation with, I don't know, maybe 50 patient models or something. You can see right from here a big variability from person to person. Okay, so we have identified data from 50 persons, and then we did the simulation. Okay, this is from the start a big problem. You can try to correlate this variation with weight, age, gender, but this is not always an indicator. Okay? You cannot a priori say that some person is going to behave like that before. Okay, so the anesthetist would like to say before he starts the anesthesia, what should be the amount of drug that he should give. But he has some idea, but this idea can change a lot according to reality. Okay, now about loss of consciousness. I don't know nothing about the brain, so let me share my ignorance with you. This is one experiment we did with the rat. You see the rat here. The rat did not die. For instance, I was there present, and after the tests, he immediately wake up, and I have a picture in which I'm looking at the mouse, and he's looking at me with an inquisitive look. And he was eating and playing with some other one and so on. So we were very careful not to create injuries or unnecessary suffering to animals. So he's sleeping. I did him a talk to make him sleep. And you see, this is a register of one of the channels of the electroencephalogram. And you see that there are parts in which you don't have activity and some parts in which you have these bursts. And what happens is when you made the rat to sleep, these parts in which you don't have activity, so they become longer. So the brain activity becomes smaller. Okay, so you can use this information together with the spectrum. If you divide, you segment the signals, and you compute spectrum, and then you compute measures from the spectrum. The spectrum changes a little bit. In particular, the entropy, and there are several indices of NMB based on the entropy, the burst suppression rate index, which is this measure of how long are you without or with a very reduced brain activity, and so on. One of the most popular is the BIS index, which is They are commercially available, not only for the bees, but for others. But we are using the bees, and you can see here the head of the patient and the bees electrodes, okay? And the bees is some secret measure, which is something, well, the guys who did it, we know that it's related to the base spectrum of the electroencephalogram signal, but we don't know exactly what is the algorithm. Anyway, this provides an index. You can see here a picture of the record of the EEG in real time and the B's index, in this case 59. Okay.
So it is, first you compute some bispectrum.
We don't do it, we have a box.
And then from that some index is computed.
Yes. But the bispectrum is inside the box, and that's it. It's not only patented but also protected from secrecy. Okay, but there are other indexes. Some of them are very known. We know more or less the algorithms, but I'm sure that inside they have some tricks that they don't reveal. Okay. So now you have two drugs. You have one drug which is an analgesic, and one drug which is an hypnotic that acts on the self-consciousness. And you have, again, these linear parts, the pharmacokinetic for both. And now the Hill equation has two inputs. So it's more complicated, but the idea is always the same. So instead of having one line, you have a surface with the output. The DOA is a function of two, because there is an interaction between the analgesic drug and the hypnotic drug. So there is the analgesic has also some hypnotic effect, which you know, because when you go out from the dentist, you always feel a little bit sleepy. No. The problem is that there are no sensors for pain, so we don't consider it. Although, well, I'm not going to speak about it. Again, you have this behavior, and with a big variability. Okay. Let's move to the second part of the talk. And the second part is related with the effects of parameter uncertainty. I will start by doing a detour to speak a little bit about diffusion. Maybe what I'm going to say is trivial to some of the people here. I'm sure it is trivial for some of the people here, but maybe for some part of the audience it will be a new thing. And then I will use one notion from diffusion models to solve the problem of propagating the state uncertainty due to parameter uncertainty. Okay? And as a product, I will use this to filter the state, to get an estimate of the state from the observations. Okay. Now, let me speak about diffusion. To understand, to explain diffusion, perhaps one model is like this. Suppose that you are a molecule, okay? You are a drop of ink. What is your name? Yes? Thomas. You are the Thomas drop of black ink. You should have brought your black coat instead of a white one. But anyway. And suppose that you have a container, which is a linear container. Okay? And I'm going to drop Thomas in the middle, okay? In the middle of this container. So you have this black drop made of molecules. And now suppose that you are no longer the whole drop, you are just one molecule. Where would you go, left or right?
50-50 chance.
That's right, you don't know. So part of the molecules go to the left, part of the molecules go to the right. So they split. After a while, they reconsider. The molecules start saying, well, why have I gone to the right? So part of them continue to the right, but the other part go to the left. Okay, and so on and so on and so on, and you get this process of diffusion. Okay? Now, how can we model this in systematic terms? Let's think this is a discrete process. Let's think about if it is continuous. So you have first order nonlinear differential equation. So this f is some function that you know. This sigma is a parameter. Imagine sigma to be 1. And v is a white noise. Everybody knows what is white noise. White noise is a signal for which the spectrum of the contents in frequency, the power is constant. That's why it is white, like the light. You have all the frequencies there, from minus infinity to plus infinity. And so V varies a lot because you have a lot of high frequencies. So V is changing a lot in a wild way. But then this acts like a filter, and X is more regular. Okay? Now, we have a problem. It's a slight problem, but we should consider it. And the problem is that this equation has no sense if you place there white noise. Why? Suppose that you think of the derivative. The derivative is this limit. So you pick x at time t plus delta minus x of t divided by delta, and in the limit you get the derivative. The problem is that with white noise the limit does not exist. Okay? Why? Because you have the power of the signal is so strong. So if you start amplifying regions that seem to be regular, they are always irregular. So you don't have, okay? You don't have a convergence. And the way you can solve this problem is awful. Don't ask me, because I know nothing about this. And you have to redefine this integral here. You write equation as an integral equation, and then you redefine this integral here. And there is a funny story, because Ito redefined the integral, and then Stratonovich made a new definition of the integral, and Ito said, well, you are not right, because there are some extra terms when you compute a differential that you don't consider. And Stratonovich said, well, you are an ignorant. Well, he was not using exactly these words. You are an ignorant because you don't understand that I'm using just another definition of the integral. Actually, there are infinite ways of redefining this integral. Okay? Let's be practical. Since we know nothing about this, we think that V is not perfectly white, but is wideband, but finite. So the power is finite. In that case, you can give a sense to the derivative. This is a so-called Langevin equation. Langevin equation. Langevin was a French physics, researcher in physics. Okay, now, we describe these stochastic processes in this way as exciting a nonlinear system with white noise. And we can ask, since X is now a stochastic process, it must have some probability density function, which depends on X and on time. This evolves on time. Okay? How can I compute this? And this solves the so-called Fokker-Planck equation. Okay? With an initial condition, which is the probability density function of the initial condition, and also you ask that this PDF goes to 0 when X goes to plus or minus infinity. Okay, so you have also these boundary conditions. So this is a so-called, in mathematical terms, a Cauchy problem, in which you have an initial distribution and then time passes, and this is deformed because you have this Fokker-Planck equation that is changing the shape of the initial condition. In simple terms, what does the Fokker-Planck equation do? You have two terms. This term here, I'm not going to show it, but it's not difficult. What it does is, dx dt, or x is changed due to the action of this vector field f. So this part here has to do with the deterministic part, okay? And it changes the PDF because X is being stretched or condensed and so on, okay? And then the second part, which is the second derivative with respect to space, has to do with this effect of the excitation by the white noise. This is, if F was 0, what you would get is the so-called heat equation that propagates the heat when you have a bar, you have a rod of metal, and you force suddenly the central part of the metal to be very hot, and then the heat starts propagating. And the solution is very simple, is the convolution with a Gaussian kernel. Okay, so we have these two things. Let me show you one simple example which is funny, which is the phase lock loop error. This appears in telecommunications. I don't have time to speak much about this, but I can write the equation. I can write the Fokker-Planck equation. So you get this effect. So time goes to your right, and this is the x level, and the phase lock loop system is suppose that you have a stochastic process, and you are making observations based on the sinus of the process. Okay, and you want to estimate the process, but the problem is that your observations are periodical. So after a while, you start invading parts where you have an error that accumulates, which is 2 pi and 4 pi and so on, and minus 2 pi and so on. That's why you have, as time progresses, the error is diffusing, and these modes here are being enhanced. Okay? So this has nothing to do with anesthesia. Now, one particular case is the case where you don't have noise. The only source of uncertainty is the fact that your initial conditions are only known in the form of probability density function. So your system is deterministic, but the initial condition is a random variable. Okay? What happens to the state? Or there is a probability that the state at time t becomes a random variable. And you just kill the sigma that appears here, because sigma is 0. This term associated to the convolution with the Gaussian kernel is killed. And you get this, and I call it the Liouville equation following Roger Brocket. Roger Brocket calls this the Liouville equation. Don't get confused, because there is another thing called the Liouville equation. Okay, so there are two Liouville equations. Liouville equation. Okay, so we have this. This is a big cannon. Okay, it's a heavy machine gun. Now let's go to the problem of propagating the uncertainty due to the uncertainty in the parameters, and start by considering a system described by a nonlinear state space model that depends on theta, but you know theta, so there is no uncertainty. And you integrate this given some initial condition, and you get a curve. Okay? Of course, if x has more than one component, then this is in a three-dimensional space. So at time t, you get an x of t. Okay? If theta is different, you get a different curve. But in each case, it's just, you know exactly what happens. Now, suppose that you start always from the same initial condition, but sometimes you use one value of t, sometimes you use another. So you get a family of curves. And at time t, you want to compute p of x of t. And this is no longer deterministic, because your initial condition for the parameters of theta, your characterization of the parameters theta is now as a random variable. So you get if you repeat the experiment, you get different curves. Okay, as in the different patients. Okay, how can we characterize this? So the answer is, okay, before the answer, you can also ask this. Suppose that you solve this problem, and you start doing observations, some function h, which is a function of x and theta. So you observe this y at discrete times. Okay, you can ask what is the probability of the state given the observations of y. Okay, so you have these two problems. Now the solution of the first problem is you enlarge, you augment the state of x by the parameters. And then you apply the Liouville equation, because this is still, this satisfies this equation, dz dt equals to capital Fc, where capital Fc is F0. There is no noise. The only source is the fact that part of the initial conditions, the part related to theta, note that I'm describing theta by a differential equation. When you speak with your girlfriend, Thomas, you can say, well, theta is 4. Okay? That's a prosaic way of speaking. If you tell her, well, theta is such that theta dot, the derivative of theta, is 0, and the initial condition is 4, you will start to see that your girlfriend will look at you with another eyes. Okay? So here I do the same thing. So I put here theta in the state, and so theta dot is equal to 0. That's a way of describing something which is constant. If I want this not to be constant, I could add here some noise, for instance, to make a random walk or something. But I'm going to make it constant. And then I apply the Liouville equation. Now this looks different, because the one that I had before was for the scalar case, and this is for the multivariable case. Okay. We can solve this Liouville equation, and we can also use a Bayesian filter. Okay? Actually, the idea of not estimating the parameters, I think the story of the parameters is new, but the story of getting this continuous dynamics filter with discrete observations dates back from the book of Jasvinsky. I think it was the first one in 1970, so 45 years ago. So you use just a basic equation. I don't have time to go through this. So I will jump this for example, and going to anesthesia. Now, instead of having a comportamental model, I have one model in which I only have this parameter alpha. Actually, this alpha, there are works that show that this represents well a big class of patients. Okay? So, and I have the Hill equation. So I apply this technique, and you can see here the different curves. So in the plane, so the state goes in the curve, goes in this plane here. These are these red curves, and the probability density of the state goes from one point and then moves to the other. Okay, you can compute them exactly. Okay, this is a kind of Byzantine problem, but you can also then complete this with. You can also complete this with the observations, and you get a filter. Okay, a filter for a continuous time system based on the continuous time dynamics and discrete time observations. Okay, and this is some simulations, and these are results with clinical clinical data. If you compare it with the extended Kalman filter, you get a slight improvement with this approach. Okay. Okay. So this is about uncertainty and characterizing uncertainty, and perhaps for some of you had the benefit of having a contact with diffusion models and the Fokker-Planck equation, and the story of treating this situation in which we have a deterministic system with stochastic but constant parameters. How can we characterize things? Now, the third part is about control of anesthesia. Let me speak a few minutes about it. I selected 3 topics. One is about multiple model adaptive control. The other is related to the situation in which you have measurement outliers. And the third one is how can we use robust control to get some simple controllers for anesthesia. Okay, let's think about neuromuscular blockade. So there is a famous book by Nicholas Verse, Algorithms plus Data equal to Programs. So sensor plus algorithms plus actuators equal to NMB control. Okay? If you have sensors and actuators and models, you can control whatever it is, whatever you think. It can be live now. You have the sensor, you have measurement data. Actually, the measurement data goes first to the anesthesia tower of equipment and then goes through the USB port to the computer, which is running here, and computes the rate at which this searing is being pushed. Okay? And the searing is infusing the drug in the patient. Now, one possibility to tackle you have basically 2 families of problems or ways to attack problems in which you have uncertainty. Or live with uncertainty, that's the robust, or try to reduce the uncertainty by learning from data, that's adaptive control. Okay? And in adaptive control you have many approaches. You have methods based on the Lyapunov functions. You have methods based on the certainty equivalence principle. You have methods based like these ones. You have a number of different controllers. And you have a supervisor that looks at the data and tries to decide which is the controller that is most suitable to be applied to the patient. Okay? How does this supervisor works? So you have a number of candidate models, okay, and use these models to generate candidate values of the plant output. You compare it with the plant output. So this Y1 and Yn are candidate values for Y. Y1 means what I expect Y to be, assuming that model number 1 is true. Okay? Same for the others, and I compare the errors using, for instance, a low-pass filter. Actually, there is a long story about this and changes to this and so on. What I would like to call your attention is this. Suppose that you have a linear system, so A and B are polynomials, or B over A is a transfer function, and E is some noise. Okay? And you can write your model like this, where AO is some polynomial that you decide. It's the observer polynomial of the estimator. You add and subtract and divide and so on. Okay? So if you have this model, well, it's natural that you say that your predictor is your model without the noise part. So the error is the noise, E, filtered by 1 over AO. Okay? And AO is something that you can decide. So you can, usually AO is something that gives you 1 over AO is a low pass filter. Okay? If you reduce the band, you are just comparing the models in the low frequency, whereas the model is acceptable. Actually, the selection of AO is the difference between the models work or not work. Okay, I will jump this. Let me show you some clinical results. So this is one clinical result and this is another clinical result. Okay, here in this case, this is the drug. Okay? And these two measures here are the primary measurement that we did. You see that there are some outliers, but somehow we managed to get rid of these outliers. And this is what we believe it's the measure of neuromuscular blockade. Okay? And here, the observer is faster. So you allow more noise to pass and more model dynamics to pass. And the result is that your manipulated variable is like this. Very shaky. If you reduce your bandwidth of the observer, then you improve. Of course, many things vary from one case to the other because we can't say, okay, we did an intervention to you, now we are going to be operated again just to compare things. So there are two patients and so on. But we have, these are simulation results that show the result. So actually this can make the difference between the algorithm work or not work in practice. Okay, one other thing are temporary sensor faults. So sometimes, this is a typical record. Sometimes you have your sensor and sometimes you jump to 100 or to 70. Usually it saturates. Now, you can imagine what happens if you have a controller connected in this situation. It says, well, the person is waking up, so let's give all the full amount of drug that we can. That's what the controller thinks. So you have to cancel this. Now, there are several ways of canceling this. They have long stories behind, but let me just make a few sentences about it. One way is we usually use quadratic criteria. No? Everything is quadratic because when we have a quadratic criteria, you differentiate it and you have a linear equation that we can solve easily. Okay? And we have a connection between a quadratic criteria and the Gaussian function. And the Gaussian function is the maximum entropy function in some cases. Okay, so everything is quite nice, but this is far from being Gaussian. This is a non-Gaussian behavior, non-Gaussian noise, heavy tails. Okay, so one thing that you can do is you replace your quadratic criteria by a linear criteria, and then the optimum estimator is no longer the average, but it's the median. Okay, so use a median filter. That's one way. The other way, if you want to play with either Markov models and so on, you can say, well, I have two states for my measurement device. One is a normal one, and the other is a faulty situation. Okay, and from the observations, I infer using an algorithm which is a classical one from telecommunications. Everybody knows the Viterbi algorithm, but this is not exactly Viterbi because this is filtering problem. Viterbi is a smoothing algorithm, and you can use this algorithm to make the estimation. And well, you have here an example in which this is the primary signal with all these outliers, and this is removed, has been removed with this type of algorithm. Okay, now just 2 more minutes to speak a little bit about control. One can use a lot of complicated things, very sophisticated, but it's always nice to think, what is the minimum acceptable solution? And we can think of this situation. We have, usually this is a regulation problem, so we want to keep the signals close to a constant value. Even if there are some variations due to noise or due to, for instance, the electric scalpel cause disturbances, you want to return to this value. So this is a regulation value. In this regulation value, essentially, you have a linearized model. Okay? And you have uncertainty. So use some algorithm that allows to control an uncertain nonlinear linear model. And there is a huge literature on that. Okay? So first, we started trying to ensure the robust stability condition and to tune the algorithm by hand, okay, without optimizing it. And this was the result. This is a clinical case. You can see that it works, but you are always. This is this is for NMB, but we have similar results for depths of anesthesia. You are always eating the boundaries, 0 and the maximum value of the drug. Okay? And it regulates, but it's not fantastic. Then we said, okay, let's optimize this and let's use, for instance, H infinity control to get a maximum flat solution. Not only the robust stability condition, but a maximum flat solution. And the result is much better. Okay? This is, again, for NMB. And you see that you no longer have this stupid boom, 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 boom. No, it's you have the value is very well behaved, and you can even do changes between 10% and 4%. Usually, you keep this for hours. You have this is 1.5 hour here, but we have records of 7 hours, and so on. The same for depth of anesthesia. Okay, so this is again with H infinity robust control, and this final example is a patient in which we are controlling both, although without any interaction. The neuromuscular blockade below. So this is the drug dose. And this is the neuromuscular blockade level. And here you have above the depth of anesthesia level. And here, this is the drug, which is propofol. Propofol became famous because Michael Jackson died with propofol. Okay, so to conclude, maybe a major message is that if you have adequate sensors and actuators, and you can build a model, you can then design controllers and control anything. Okay, without sensors, forget about it. In the case of anesthesia, you have big parametric uncertainty, noise, and non-Gaussian noise. You have the story of the outliers. You have to be careful about it. And you can explore the venal model structure and perhaps some other things, like positivity and the fact that you are controlling the mass and so on. I was not involved in that personally, but some other, Teresa Mendonça for instance, developed a constant mass controller. The other thing is that simpler but robust controllers are preferable than sophisticated but complicated things. And what about the future? Some problems. One is use genomic information a priori, taken a priori, so that you can incorporate more data when you initialize the algorithm. Pain measurement and control. I think this is going to appear. There are some tentatives. For instance, pain is a complex process, but it's related to the rate of change of the depth of anesthesia signal. I've seen a situation in which they had a differentiator with a low pass filter, and they were doing like this to the patient, and this was increasing to a different level. Well, just like this, no, not really big pain. So, but this is not the whole story. So, and there are no commercial reliable sensors, no commercial sensors at all. Another thing is light sedation, situations in which people that suffer, for instance, from cancer, and they control themselves the amount of drug they give to themselves, using models and using control techniques to help. So instead of the person when pushes, somehow this is optimized and use some information from their bodies. And ready to use automated anesthesia for animals is also, in many cases, is the medical doctor, the veterinarian that anesthetizes the animals, and sometimes this is too much or too less because they are not professions of that. And for animals it costs a lot to have a team, a full team of, you can't afford to have that. So if you have some reliable but simple devices that could be used by veterinarians, it could be some opportunity of work and poses some different problems. Although the anesthesia for animals is essentially, apart from the quantities and the fact that animals have hair, so it's very difficult to place the sensors, but essentially they are the same models and the same problems. We had some experience in one of the projects. Thank you very much.